Boa noite a todos, sejam bem-vindos a este webinar. Ele é organizado pelo capítulo do Brasil, da IGS, em parceria com a Geotecnia Brasil. Meu nome é Carla, eu sou engenheira geotécnica e muito feliz de representar a IGS Brasil. Nós estamos muito felizes em ter vocês aqui. Depois da apresentação, nós vamos ter uma sessão de perguntas e respostas. Essa live vai ser em inglês, então a partir de agora eu vou falar em inglês e a apresentação também será em inglês. So, hello everyone and welcome to today's webinar organized by IGS Brazil chapter in partnership with Geotecnia Brazil. My name is Carla Maia. I am a geotechnical engineer and proud to represent the IGS Brazil chapter. We are truly happy to have you with us. After the presentation, we'll have a Q&A session, and your interaction makes this session even better, so don't hesitate to contribute, join the discussion, and post your questions in the chat. Our session will be moderated by Professor Enio Marques Palmeira. He is Professor Emeritus at the University of Brasília in Brazil and a leading specialist in geosynthetics. Thank you very much, Professor Enio, for accepting the invitation to moderate this session. It's an honor to introduce Dr. Richard Bathurst, Professor Emeritus of Civil Engineering at the Royal Military College of Canada and Visiting Research Fellow at Japan's Port and Airport Research Institute. Dr. Bathurst has authored over 230 peer-reviewed papers and led major societies, including Engineering Institute of Canada and the International Geosynthetic Society. He is editor-in-chief of Geosynthetics International and the International Journal of Geomechanics. Honors include Fellow of the Royal Society of Canada, the Thomas A. Middlebrooks Award 2021, and the Julian C. Smith Medal. So, Dr. Bathurst, please go ahead. It's an honor for me to be in the session with you. Thank you very much.
Thank you, Carla, and thank you, IGS Brazil, for inviting me. It's always a pleasure for me to talk to my friends in Brazil, including my long-term friend, Professor Enio Palmeira. I have often mentioned to Enio that I do have a Brazilian connection. My mother is Portuguese, and her father, my maternal grandfather, was born in Portugal, and like lots of young men early in the 1900s, he was shipped off to Brazil, and he spent 10 years working in Manaus. So there is a connection. Anyway, I thought I would start by just telling you a little bit where I am. I'm in Kingston, Ontario, which is shown on this map. And it's currently about 15 degrees below zero, and there's a blizzard of snow outside. So I'm quite jealous and envious of all of you there. I have spent my career at the Royal Military College of Canada, located in Kingston. And this is probably the smallest university in Canada. It's a little bit, I'm sure you have a military school in Brazil. It's a little bit, it's equivalent to West Point in the United States. And its principal objective is to graduate students who will become serving officers in the Canadian Armed Forces. However, it also, as part of their program at RMC, they graduate with a certified civil engineering degree, just like you would at a civilian university in Brazil or in Canada. And we also have, as part of our degree programs, master's and PhD programs. And so with that environment, and also with a physical a relationship with Queen's University in Kingston, we do the type of research that one would expect at civilian universities, even though we're the Royal Military College of Canada. So my topic has to do with mechanically stabilized earth walls.
Oh,
And
sorry, Mr.
yes,
You don't put your presentation. Your screen for me is not in your presentation.
are you seeing anything at all?
I'm just seeing like the scream yard scream. I'm not seeing the presentation.
Are you seeing my presenter view? Are you seeing a
Yeah,
screen with, okay, that's what you're
yeah,
seeing? Okay, so I just need to switch that over. 1 second.
yeah. Thank you. Sorry
Had
to
it,
interrupt you.
no, it's fine. I just have to get this thing. Oh dear. Okay, I'm just going to have to start again here. Oh no, there we are. How's that?
Not yet.
Okay, let it.
If you want to stop to sharing and
Yeah, I
try
think
to
I'm going to have to.
share again,
I'll
yeah,
stop and then start
you'll be
again.
better.
Yeah.
Just technical problems happens.
Yeah, this happens. Okay, let's try again.
Yeah. It's not yet. I'm seeing like the StreamYard uh screen, not the presentation.
Are you seeing yourself?
Yeah.
Okay, so it looks like it's not coming through. That's strange. I'm sure I'm doing everything right. Hang on, let's try this again.
Yeah.
Oh, just, I don't know what's happening. Stop, start, share. Share.
I'm still seeing myself.
This is very strange.
Yeah.
How about, are you seeing something different now?
No, it's still the same.
Oh my
But it's
goodness.
weird because we make like the test and the test was right.
Yeah, no, it's, I
Yeah.
guess I shouldn't have, okay, just a sec.
Oh.
I am, I'm a little bit lost as to what to do next.
Um, you are sharing the full screen when you put to share,
Yeah.
and you are sharing a window. Or
Yep. I'm going to turn it off and do it again.
yeah, try to don't share just a window. Try to share the full screen to see if make better. Oh yeah, now it's work. Now I can see your presentation.
Okay,
Yeah,
so you
perfect.
can see the present. Okay.
Yeah, and everybody can see right now.
Okay.
Yeah.
So
So
much
you
for
can.
our practice. Okay. So,
Yeah.
um,
Oh yeah.
so my
Sorry for
topic,
the interruption and
I'll
everything.
start again, sorta. So the topic is migrating to reliability-based design of MSE walls. And I was talking to myself. Did you hear my verbal presentation previously or not?
Yeah, everybody here, they
But they
just
couldn't
don't
see the
see.
screens. Okay.
Yeah.
So these were the slides that I was speaking to that show the location of Kingston and the Royal Military College of Canada. So I've spoken to those slides. So now let's get on with the business. So the topic of my presentation is related to mechanically stabilized or MSE walls. And these systems have been around for a while. So there's no new technology in the slide presentation that I'm going to make. And but I introduced the topic by remembering that these MSE walls are constructed both with inextensible and relatively extensible polymeric reinforcement. And it's always fun to look back over history and see from where this technology came. And I like this slide because it actually shows the first steel reinforced wall with a concrete panel face. And this was constructed in 1971. And here you can see the steel strips that are used to stiffen and strengthen the reinforce the fill soil. And this technology persists to this day. In fact, here is an example of a very impressive tiered steel strip MSE wall in Washington State, and it was the highest wall of its type, if I remember correctly, at the time that it was constructed in 2006. So you can see in the little insert figure again the concept of using these steel strips to strengthen and stiffen the soil so that it can behave as a monolithic block. And other types of steel reinforcement have been used for the same purpose. This includes, for example, steel ladders or steel mats. And the idea, the notional idea behind these MSE walls is that if you stack a granular frictional soil up, it'll form a pyramid shape, but the maximum slope of that soil is its angle of repose or its friction angle, if you like. And if you want to construct a vertical change of grade, then a strategy is to introduce perhaps layers of paper in this laboratory example. And this is, if you like, a type of artificial cohesion that allows you to construct these near vertical structures. Now, of course, we don't use paper. We have developed as an industry high performance polymeric materials that we call geosynthetics. And this internal reinforcement can comprise, for example, woven geotextiles. And they've been used for many, many years. And the first walls that were constructed using these so-called geotextiles had this type of geometry. Horizontal layers of reinforcement were placed in a backfill and then wrapped around the face of the structure and tucked back in order to stabilize the face. And then these layers were placed in sequence until one constructed a monolithic block to perform the retaining wall function. This slide is one that I like to show to my friends in North America. This is actually, the photograph is of the very first geotextile wrap face wall constructed in North America. The United States Forest Service was enamored of this technology because it allowed them to get into hard to reach areas to build earth retaining structures in hard access spots, like for example to support a unpaved road over a gully or swale, as you see here. And the cross section for this wall is shown here. And in fact, it was interesting. A few years ago, the original designers of this wall went back to this wall after about 30 years and exhumed specimens of the geotextile and tested them, and were able to show that the materials still had enough strength and stiffness to perform the retaining wall function. Much larger wrap face walls have been constructed, obviously, since that time. This was the highest wrap face geotextile wall in the world at the time it was built. And it was the face, the geotextile faced wall was actually used to support the sides of a preload, which was used to compress compressible organic clay soils at the location of a bridge overpass. So this wall was temporary. I think it was in place for something like 2 years. And again, the cross section, you can see the wrap face construction. And in this particular case, 4 different types of geotextiles were used with decreasing strength and stiffness as you went from the top of the wall to the bottom. Now, more common, it can be argued, are the use of geogrid reinforcement products, which are made from HDPE or polypropylene or coated PET construction, as you can see here. And there's a wide variety of these materials around. These geogrid materials have been used to construct full height panel concrete faced walls. So to the layperson, this looks like a conventional tiered concrete gravity wall, but behind each facing are these layers of geogrid, and in this particular case, it's a uniaxial HDPE type, and that's the magic that's going on behind these walls. More recently, we've seen the use of polyester strap reinforcement, and you can see the material up in the corner here. They come in rolls. The reinforcement comprises parallel aligned polyester yarns, which are doing the work, and they are coated for protection and stability using polyethylene sheeting. So it comes in rolls, and they unwind it and place it in a W pattern. But the reinforcement is performing the same strength and stiffness function that the geotextiles were and the geogrid materials were that I showed you in the previous slides. From a mechanical point of view, these MSE walls are essentially composite gravity structures. They form a mass or a block which resists sliding and overturning due to the pressures and loads behind this block developed through the retained soil. And in order for these reinforced soil masses to function, they have to be internally stable. So that means that the reinforcement mustn't rupture or strain internally to failure. And we imagine that happens along an internal active Rankine failure surface. We don't want the reinforcement to rupture at the connections, and we don't want the reinforcement to pull out of the soil, which is imagined to exist in a passive zone behind this internal failure surface. And a main challenge in the development of design methods for internal stability has been how to calculate the maximum tensile load in the reinforcement under operational serviceabilities. serviceability conditions. Okay, this is the day-to-day conditions that the retaining wall must perform adequately. And before we get into details, we have to introduce the analytical equations that we associate with the internal stability limit states for these walls. So, for example, we have to be able to calculate what is the nominal load, tensile load, which is developing on this reinforcement layer. And that's on the load side. And just a sec. So here's the a typical equation to calculate the nominal load in the reinforcement, and you can see it's proportional to the spacing between the reinforcement, some equivalent lateral earth pressure coefficient, and the vertical stress acting at the elevation of the reinforcement. On the resisting side, we have pullout, and here's a typical equation for pullout that says that in this passive or resistance zone, the pullout capacity is proportional to the length of the reinforcement and the vertical pressure, etc. And then we have to have a nominal resistance, which doesn't exceed an allowable tensile capacity of the reinforcement. And we want to make sure that the load in the reinforcement is not so low, or high, to cause the internal soil failure mechanism developing in the wall. Now, in the olden days, which means when I was an undergraduate student, margins of safety were expressed by nominal factors of safety, which meant that knowing the nominal resistance for any limit state and the nominal load for any limit state, we want to make sure that the ratio of those two values is satisfactorily greater than 1. Okay, and that's typical of working stress or allowable stress design. When we use modern design codes in North America, these are all based on load and resistance factor design concepts. And here you can see the current code for the US on the left. And we in Canada have an equivalent LRFD design code, which you can see on the right. And in these codes, instead of using a ratio of nominal resistance to nominal load, we use a factored nominal resistance and a factored nominal load, where the nominal resistance is multiplied by a resistance factor, which is 1 or less, and the nominal load is multiplied by a load factor, which is 1 or greater. And for a limit state to be satisfied, this equation has to be greater than 0. And if you use LRFD and you satisfy this equation, it guarantees that you will have an adequate margin of safety. Now, here's the problem. Let's imagine, let's go to the top left here. Here's my nominal load and my nominal resistance. And my factor of safety will be greater than 1 as long as the nominal resistance is greater than the nominal load. And if the nominal resistance is much larger than the nominal load, then I will have a larger nominal factor of safety. But what we need to admit and understand is that these estimates of nominal load and nominal resistance have some uncertainty. So if you had a large number of these nominal loads and nominal resistance estimates, there is the possibility there may be a combination of nominal load and nominal resistance in which the nominal load is greater than the nominal resistance, and therefore our limit state is not satisfied. And if the nominal load and nominal resistance are very different, the possibility of the nominal load being greater than the nominal resistance is much less. And the red area that you see here is a notional idea of how large that probability of failure may be. Now, if we look at the bottom left, what you see here again are the same best estimates of nominal load and nominal resistance, but here the uncertainty in each one of those values is actually much larger. And here we have greater probability of failure than the cartoon that you see above here, even though our conventional nominal factor of safety calculation is the same. And again, you see here, this is larger probability of failure, even though the nominal loads and resistances that we calculated at time of design remain the same. So this provides the motivation for reliability-based design for internal stability of MSE walls. Reliability-based design addresses and quantifies uncertainty at the time of design within a probabilistic framework. It provides a more nuanced appreciation of margins of safety for soil structure interaction problems compared to limit state design using deterministic factor safety past practice, load and resistance factor design, and partial factors approaches. Okay, a more nuanced appreciation of margins of safety. And so how can we quantify these margins of safety probabilistically? Well, we use a concept called reliability index, which is given the Greek symbol beta. And here I want to show how we calculate this reliability index. If I know what my best estimate of load and resistance is, and I have an idea of what the spread and the uncertainty is in each of these nominal values, I can quantify it by a coefficient of variation, which is just the standard deviation divided by the mean. And in this equation, I can enter my deterministic factor of safety, nominal factor of safety here. And if I know what these coefficients of variation are for my estimates of load and resistance, I can put them into this equation. And out here, I can calculate what the reliability index is. The higher the reliability index value, the safer the limit state within a probabilistic framework. And it doesn't matter what the statistics are, what the mean and of the nominal load and resistance are, or the best estimates. As long as I have the spread, an estimate of the spread in these values, I can put it into this equation and calculate beta. Now, some people may have problems with reliability index, but it is mathematically relatable to the probability of failure. And here's a plot that shows probability of failure versus reliability index. And there's a mathematical relationship between the two. And what it shows is, as the probability of failure gets smaller and smaller, the probability that my limit state is not going to be satisfied, as it becomes smaller and smaller, then the reliability index value goes up. So that's what I said, is that a large value of reliability index is better than a small value. And this is the vocabulary that is used in structural design. The beta, if I write this performance function, instead of writing just focusing on the nominal factor of safety, if I write nominal factor of safety -1, I have this performance function G. And if G equals 0, then I'm at limit equilibrium. And Beta times the standard deviation of this distribution of G is just the distance between 0, the limit state is just at failure, and the mean value. So this area that you see here is the probability of failure, and this is beta. And this shows you, at least visually, the connection between this reliability index term and probability of failure. So what are typical values for design? Well, if we're dealing with typical foundations, and we're interested in the probability that base sliding is not satisfied, then typically we might use a probability of failure of 1 in 1,000 for design, which maps to a reliability index value of about 3. So these are the relationship between probability of failure and reliability index. Now, for internal stability of our MSE walls, a much lower reliability index value and a much lower probability of failure is acceptable because these structures are highly strength redundant systems. In other words, if one reinforcement layer does not satisfy a limit state, there are other neighboring layers that can take the load, as it were. And that's why we're able to use a lower factor of safety and a lower reliability index for reliability design of these systems. So here's the slide that we saw before, but now let's look at how can we estimate what the spread or the uncertainty is in our estimates of nominal load and resistance. Well, let's look at this nominal load equation that you see here. There is some uncertainty in this value. That's because if you look at the equations for unit weight and for this coefficient of equivalent lateral earth pressure, they are functions of friction angle and unit weight. And these values have some uncertainty. I may pick a friction angle that's different from the friction angle that Ennio may pick. So there's some sort of uncertainty. And there may be some uncertainty about the applicability of this model for this particular project. If there was only uncertainty in the friction angle and unit weight, then I could calculate COV of the load and the COV of the resistance directly, just using some simple equations. And the same uncertainty with nominal values for the resistance side also apply. Okay, so this is what I mean by uncertainty in the estimate of the nominal load and the nominal resistance. So how do we quantify these values? Well, in Canadian practice, there is the notion of level of understanding. And this concept is holistic. It gathers together all of the sources of uncertainty that we have when we calculate our nominal values at time of design. So, and they're grouped into high, typical, and low levels of understanding. Typical understanding is exactly what it means. For typical projects where you have a typical amount of test data and experience and the design methods are typical, then we would have a typical level of confidence in our predictions for the design of these systems. If we had more site data and more experience and with this type of technology, then you could convince someone that you have higher understanding. And then the reverse is true. If you're doing a design where you have less data than you would like to have, less experience, etc., then you could argue that you have a lower level of understanding. And this is actually codified in the Canadian LRFD design code. So that's nice, that's qualitative, but I need hard numbers for the spread in the estimate of the nominal load and the spread in the estimate of the nominal resistance. And what we have done is we have chosen for a typical level of understanding COV values of about 20%. If we have high understanding, then we can use a smaller value of COV because the width of these distributions for load and resistance are smaller. And if we have low understanding, then we would use a value of 30% for the COV of these nominal values. So these values that you see here, the COV values, can then be put into this equation that I showed you earlier, together with our best estimate of the nominal factor of safety, and this will give us a reliability index value. So thus far, we've assumed that the load and resistant models are perfect. Okay, the only uncertainty we have is in the input parameters that we're going to put into the model. But the model itself, we are assuming is perfect. And so we've assumed that all of the uncertainty is at the time of the design is in the choice of the nominal values at time of design, based on overall level of understanding. But there are other sources of uncertainty at time of design that we need to talk about, because there is always some error in the underlying deterministic models for load and resistance. We call this model bias. This is error which is independent of the project that you're designing for. It is the intrinsic error in that equation that you're using to calculate the nominal load or the nominal resistance. And this is a particular concern for internal stability limit states for MSE walls, because all load and resistance models have a large empirical component. And there are different models to choose from, and the accuracy of those models can vary widely. And it can be shown that model bias, the inherent accuracy or inaccuracy of these models, has a greater quantitative influence on computed margins of safety than the uncertainty in the choice of the nominal input values that you use at time of design. Now, fortunately, and MSE walls in some ways are a great opportunity to test these ideas of model bias, because we have lots of data, and we can use this data to quantify model error for things like tensile rupture and pull-out limit states for MSE walls, for both walls with extensible and inextensible soil reinforcement products. So we go back to this slide, which we've seen before, and we ask ourselves, well, what is the model error for the calculation of nominal load? What's the error by just using this equation? Well, we answered that question over many decades by going into data taken from walls in which, for example, for steel reinforced walls, people had put strain gauges on the steel, and from those strain gauges, the loads in the reinforcement under operational conditions could be deduced. And from this, each one of these measurements, from each of these instrumented layers, we calculated the measured value. And then we calculated the predicted value for this layer using whatever model we were interested in this comparison. So this is the AASHTO simplified method. And we put that predicted value into the denominator of this ratio, which is bias, and calculated the bias value. So depending on the model, there are different coefficients for the equivalent lateral earth pressure. If you use the simplified method in AASHTO, for example, in order to predict the maximum load and the reinforcement in this layer, I would go to this design chart here, and knowing the depth of the reinforcement, I could go to this chart, and from the horizontal axis, I could deduce what this equivalent earth pressure coefficient is using this ratio of Kr to Ka, where Ka is simply the active Rankine earth pressure coefficient. And all these design methods are variations on this theme. So now we collected all of these measurements from 97 of them from 24 different steel strip MSE walls. In fact, I think we have more data now than when this slide was constructed. And I get a distribution of these bias values, and they invariably follow a log normal distribution with a mean and a COV. And so in this case, the mean is 1.19 of these bias values, and the spread is about 40%. And we did the same thing for geogrid walls. And here's a wall that I was involved in, actually. And from each layer of reinforcement, we had a bunch of strain gauges. And from those strain gauges, we were able to deduce what the maximum measured tensile load in that reinforcement layer was under operational conditions. We compared that to the predicted value using different load models. And from that data, we could then gather the statistics for the bias values. So for example, using the stiffness method, the mean value was 1, and the spread in the load bias values was about 30%. Now for the resistance side, we did the same thing. So what we're interested here is what is the model accuracy when one uses a linear pull-out model, which is very common in the literature and in the design codes in most countries. So the way that we got the measured values is that we collected data from pull-out box tests. And this shows the pull-out test apparatus in our lab. Most of you are probably familiar with these pieces of equipment. Essentially, a reinforcement layer is buried in the soil of interest, and then a loading system, preferably an air pressure bag system, can be inflated to fool the soil into thinking that it's at a greater depth, as one would expect in the wall. And then the reinforcement is pulled on at the front until it pulls out of the soil in this test apparatus. That's the pull-out capacity. So here, for example, the top left slide, here's the reinforcement laid out on top of the bottom half of the soil mass. It then exits the front of the pull-out box, and here is where we pull on the reinforcement. And we can develop response curves like this that show the pull-out force plotted against displacement. And when all the extensometer points are moving at the same rate, that's the pull-out capacity. And this photograph here just shows the same specimen when it's being exhumed at the end of the test. So we gathered lots of that type of data, both for GeoGrid products, for example, PET straps. And here is an example of a pull-out test in which the reinforcement is a welded wire mesh. And again, for each test, we measured its pullout capacity, and then we divided it by the predicted pullout capacity, and that gave us the bias statistics for model accuracy. So here you can see that on average from all of these tests, the mean bias value was 2.43. This means that on average, when you use this pullout model with these materials, the measured pullout capacity is about 2.5 times the predicted capacity. So this model is hugely conservative for design. And I think a lot of us that have done MSE wall design have experienced this situation. It also explains in part why we don't typically see these MSE walls failing due to pullout. So what we can do is, if we assumed that all of the uncertainty in our limit state design was due to the model, we could write an equation like this to calculate the reliability index value as a function only of the uncertainty in model accuracy. We previously had looked at the case where the only uncertainty in a limit state design function was the choice of nominal values. We saw this equation before. And what we did simply is we just glued these two equations together, if you like, so that we could have a closed form solution that gives us an estimate of what the reliability index is, considering both uncertainty or variability in the nominal load and resistance terms at time of design, plus the inherent uncertainty and accuracy of the load and resistance models that we're using, and also consider possible correlations between model accuracy and predictions of nominal load and resistance. And it all collapses into an equation that you see here, which may be a little frightening when you see it initially, but it is actually a thing of beauty, because if you color code it, you can see visually what the different contributions of nominal load and resistance uncertainty and uncertainty in the bias values influence the calculation of beta. And this equation is valid as long as all of these quantities are log normally distributed. And we've been able to show that that is a reasonable assumption. The other thing about this equation is that you can rewrite it and you can place these statistical quantities into coefficient terms A and B. And when you do that, this equation shows that the reliability index is proportional to the nominal factor of safety. This says that as the nominal factor of safety goes up, this is the value of nominal factor of safety at time of design, beta, the reliability index, also goes up. I think we'd all agree that that makes intuitive sense, but here, for the first time, is a quantitative link between reliability index, which is a modern concept in probabilistic design, and nominal factor of safety, which has been used in past practice for the design of geotechnical structures. So it's and the other thing about this equation is I didn't have to do any Monte Carlo simulation. And my experience has been, and perhaps everybody in the audience, is that as soon as you mention Monte Carlo simulation as a requirement for design of a structure, it puts many engineers off. The advantage of this method that I've shown you here is that I can put this equation in a spreadsheet, and I can do parametric analysis without having to resort to Monte Carlo techniques. So going back to the LRFD codes in North America, these codes include different analytical models for calculating the load in a reinforcement layer under operational conditions and the resistance side, for example, pullout. And one of the things that's happened in the States and in Canada is that both countries have adopted the stiffness method to calculate the load, the nominal load in reinforcement layers in MSE walls. And a signature feature of this approach, as the name suggests, is the use of the creep-reduced tensile stiffness of the reinforcement as a key parameter to compute the magnitude of reinforcement loads under operational conditions. And this is a paradigm shift from the simplified method, sometimes called the wedge method, a whole bunch of different names to it, which were based mainly on the strength of the soil. But if you look at the data, what you find is that it's the stiffness of the reinforcement that is a critical parameter influencing the actual load in the reinforcement. The soil strength is a secondary effect. So much of the work that I've done with my students and other colleagues is to develop this stiffness method. And the stiffness method is illustrated here, the simplified method. So this top formula that you see here is basically the simplified method that we saw earlier. And our philosophy was, let's sort of keep the same simplified method formulation in order to ensure a comfort level with designers, but let's modify each of those parameters with these empirical coefficients that you see here. And I don't want to spend a lot of time on this, but basically we fixed the simplified method so that it made better predictions of observed maximum loads and reinforcement layers under operational conditions. And this stiffness method was much more accurate, and you can appreciate that by just simply visually understanding what's happening in these two plots. What you see on the left-hand side is the AASHTO simplified method. And what we did with a whole bunch of data that we collected is we plotted the measured maximum load against the predicted value. Now, if it was a perfect model or a reasonably accurate model, we would expect these data points to follow closely this one-to-one correspondence line. They clearly do not. With the AASHTO stiffness method, which is this equation you see here, you can see that the measured versus predicted values are much closer. That means that the mean of the bias values are closer to 1, and the spread in the bias values are much lower than for the same data points using the AASHTO simplified method. So this equation is much more accurate. And another advantage of this equation is it can be used for both geosynthetic and steel reinforced soil walls. Okay, so it actually allows us to move seamlessly across design methods that use different reinforcement types. Now, in many cases, For example, if we have an unsurcharged wall, the wall is essentially vertical. We use the same reinforcement type throughout the height of the wall, and the soil's cohesionless, then this equation becomes simplified. And so for most walls, the equation that one would use for design is shown here. And it's not very much more complicated than the simplified method equation. So we can put the statistics for the simplified method and the stiffness method into this mother equation that I showed you before to calculate what the reliability index is for each reinforcement layer and the corresponding limit state. So here we have plots that show the calculation of reliability index for the tensile strength limit state for geogrid MSE walls. So on this plot, we have on the vertical axis here, reliability index. And here I've identified a reliability index of 2.33, which is a target probability of failure of 1 in 100. So, and on the bottom, I have plotted the nominal factor of safety. And remember that the reliability index is proportional to the log of this value. So that's why there's a log scale. There are 3 curves here. Each one of these curves is a solution for this equation using a different value of the nominal load. And so here you see 0.1, 0.2, 0.3. So 0.2 represents a curve with typical level of understanding. The curve at 0.1 represents a high level of understanding. And this curve here represents a low level of understanding. So an engineer could use the charts in this way. I want to satisfy a target beta value of 2.33. I'm interested in a typical level of understanding. That means that my nominal factor of safety at time of design has got to be close to 2 if I'm using this simplified method. I could work the other way. I could start with my nominal factor of safety and then go up to these curves and read off or calculate the actual beta value. And I can do this for the stiffness method as well. Okay, and so you can see this, same type of example, but the curves are different. So let me show you how this can be done in practice. What I want to do is I'm interested in calculating the true margins of safety for as-built MSE walls. And the first example is are a set of walls that were constructed in Washington State. So this is on the west coast of the U.S. and the Canadian border is shown here. Just a sec, my cursor is quite sluggish. But you can see the Canadian border just below the top inset label. And the project involved a pair of MSE walls that were supporting an approach embankment for a bridge going over a river. And you can see in the photograph, you can see one of the walls. This is wall C. It's about 11 meters high. And in the top right-hand plot, you can see a cross section of this wall. Actually, and I think it's the short wall there. And the neat thing about this project was myself and Tony Allen were allowed to design these walls using the new stiffness method and to instrument it in order to ensure that it was working properly, but it also allowed us to collect data to investigate the true margins of safety for the internal stability of these walls. So here you can see in the bottom left, you can see some of the instrumentation. These are extensometers that were attached to these, some of the layers of reinforcement. The top right plot shows some of the reinforcement. And then the bottom right plot here gives an example of the measured strains at the end of construction. And you can see there, the largest strains are close to the connections and then they peter out. As an aside, in many walls, the maximum strains are actually at the back of the facing because the backfill soil tends to move down with respect to the relatively vertically rigid wall. The other thing that you can see is that under operational conditions, the strains are quite low. You can see they're less than 1%. So we were able to take the data, we were able to take the nominal factors of safety that were used at design, stick it into this mother equation, and using different levels of understanding and the bias statistics for these type of geogrid walls, we were able to calculate what the reliability index was for the tensile strength and pull-out limit states for all the layers in that wall. And here's a plot. And what this plot, if we look at the colored plot here, the vertical axis is normalized depth of the layer below the top of the wall. And the horizontal axes are reliability index and probability of failure. Again, remember, they're connected. And what we have here is the target value of 2.33. If we calculated the nominal loads using the simplified method, you can see that the values for tensile strength limit state are much less than the target value, maybe only at the top where we okay. If, however, we calculated the nominal load values using the stiffness method, which is more accurate and less conservative, we were able to ensure that the reliability index, back calculated reliability index, was greater than the target value, meaning that we were safe from a probabilistic point of view. So the simplified method was unsatisfactory, and the stiffness method was fine. And actually, this is not a surprise because the wall was designed using the stiffness method and not the simplified method. Now, closer for you guys, we looked at other walls around the world, and we came across this Impalo polyester strap wall, which is fairly well documented in the literature. So the photograph shows the facing. It was surcharged. It was experimental program, and the left-hand side diagram shows a cross section of this wall. And we did the same type of calculations that I showed you before, except here, for example purposes, we're looking at the pull-out limit state. So in the pull-out assessment, we looked at 3 different pull-out models. Okay, the one that we're most familiar with is pull-out model 1. And for the calculation of load, we used the AASHTO coherent gravity method. We did these analyses for different load models, but just for example purposes, I'm showing the load model for the AASHTO coherent gravity method. And on the left-hand side first, you can see the distribution and magnitude of the beta values and PF values for each layer. And red means bad. And you can see that at the top of this wall, if you use the conventional linear pullout model for these PET straps, and you use the coherent gravity method to calculate load, you can see at the top we have an unacceptable margin of safety by a tiny bit. And if we go to this plot here, we've simply plotted the reliability index versus nominal factor of safety using this linear form of our beta equation. And each one of these symbols is one layer, one calculation. And you can see that they plot along a straight line, as we would expect from this model. And here you can see the top two layers of this wall were close to or below the target value. And this tells you what to do. Okay, what you want to do is you want to move these points up this line. And the simplest thing to do is just to lengthen those reinforcement layers at the top of the wall. That's the easiest thing to do. So this plot and its interpretation gives you design guidance on how to improve the margin of safety in pullout using a probabilistic approach. So from this talk, there's a bunch of important conclusions and impact. As I said before, reliability-based design gives a more nuanced appreciation of the margin of safety for internal limit states for MSE walls compared to conventional factor of safety or partial factor of safety or LRFD approaches. The accuracy of the load and resistance models and uncertainty in the magnitude of nominal load and resistance terms at time of design is considered explicitly. And you may be asking yourself, well, where do I get these model bias data from? Well, that, from 20 years of work, we have collected model bias data for different types of reinforced soil walls, including those with geogrid strips, steel grid, polymeric straps, and for different design, load, and resistance models. They're all available. One of the nice things about this approach is that differences in beta or probability the limit state is not going to be satisfied are detectable between walls of similar design and between different types of MSE walls that can perform the same function at a particular project. The calculation of the reliability index can be done using a spreadsheet. You don't have to do Monte Carlo simulation. And as that mother equation that I showed you demonstrates, the method provides a quantitative link between the conventional factor of safety, which is familiar to geotechnical engineers, and reliability index, which is used in contemporary probabilistic analysis and design of geotechnical structures. Before this work, there were two separate solitudes. There were the people that worked using deterministic nominal factors of safety, and then there were people that were into probabilistic methods, and they were two separate groups. Now, there are some important caveats. These bias values have been collected from actual full-scale real walls. And for your particular project, you can only use those bias values if your project falls within the envelope of the walls that were used to develop the bias statistics. And this last caveat is that the probabilistic approach to internal stability limit states for this of MSE walls should be viewed as a complementary approach to factor safety, partial factor, and LRFD approaches. So I'm not saying abandon the way things are done currently and in the past. I'm saying that this is a complementary approach. It gives you a different view with which to assess your design without throwing out, outcomes based on what people have been doing for many years and for walls that have performed okay. And this statement is written actually into the Canadian Code. Okay, basically the Canadian Code now says that you can use this reliability theory-based approach that I've just described to you. And what I'm hoping in my lifetime is that we will move fully to probabilistic and methods of design. So the data, the bias analyses, the models that have been developed within a probabilistic framework have all been published in the peer-reviewed journal archives. So here's just one paper that talked about reliability-based design for geosynthetic reinforced walls. And if you go to my website, you can find these papers that describe the development both of the underlying models and also the collection of bias data and how probabilistic calculations can be done. Now, like all professors, this work has been done in collaboration with other hardworking people, and they're shown here. Some of them are other professors like these guys here, and this row here shows pictures of various PhD students and postdocs, some of them with very bushy mustaches. Bing Wong, if you people use the GeoStudio suite of programs, he's the main programmer. If you guys use Rock Science, seen as the main man for their suite of programs that you use, and the rest of the folks here have made major contributions. I also was very fortunate to work with Professor Yoshi Miyata, who is at the National Defense Academy in Japan. And he has before I retired, he has the exact same job that I had at the Royal Military College, and fortunately, the same interests. And so he was able to work with me to use lots of data that was available in Japan for the assessment of MSE wall designs, etc. And as a sidebar, it's very interesting. In Japan, if you want to market an MSE wall system, the Japanese government makes you build full-scale walls and instrument them and take the walls to failure before you're allowed to sell that system. You have to prove it's going to work. Well, decades of that type of testing has resulted in a whole bunch of data, and that data has been used to inform the development of the stiffness method and to collect databases for model biases. And then finally, the other guy who's really important to this whole project is Tony Allen. And Tony has recently retired as the head geotechnical engineer at Washington State Department of Transportation in the States. But he was, until recently, he was the chair of the technical committee on foundations and walls and for the AASHTO manual. I showed you a picture of that. So here was a guy that I was able to work with, and it was the first to say, okay, here's the problem. This is what we need to do. Do you want to help? And for the last 30 years, we've been working together. So this has truly been an international effort and a very fine example of how much you can get done if you work in a collaborative environment with other capable persons. So I thank these people for working with me. If you're interested, as I said, in any publications, I have a website which is here. You can find me. You can Googleate me and find me very easily on the web. You can find this web page, and I'm more than happy to send you papers if you're unable to get access to them in the various journals. So, obrigado. Thank you very much for your attention. I hope you've learned something from this. And this has been my pleasure to give this presentation. Thank you.
Well, thank you very much, Richard, for the excellent presentation. And I think Carla will pass us any questions. In the meantime, I would like to ask you. Well, you base your studies on a large number of case histories, isn't it?
Yes.
Do you have an idea on how many walls did you use, and I believe from different countries as well, and different conditions, different types of soils? So can you give us an idea on how many walls and how many different conditions did you use in your studies?
Literally hundreds, but we only used walls that satisfied AASHTO criteria and specifications, because we were motivated by trying to improve models for AASHTO, and AASHTO has some fairly tight specifications. So we for any walls that had like I said, they had to fall within those specifications. So there were many hundreds of them. Now if you look in the papers, there are a couple of main papers which have tables in them, and they carefully identify the geometry, the reinforcement type, and the source of where we got the data from. And that's why I'm saying there are hundreds of them. I can't remember how many there are exactly. Some of the slides hinted at 99 data points and 27 different walls, but those were actually relatively early in the investigation. We have continuously updated those databases, and one of the reasons that we did it was that we wanted to develop a variation of the stiffness method that could be used, for example, in Japan, where they have frictional cohesive soils. So we had to use some data from that country, but we had walls from Brazil,
Mm-hmm.
And most recently I showed you those pet strap ones.
Mm-hmm. Okay.
So it was a huge project. I would say about, I'm trying to, it's like, 25 years to 30 years of work.
Mm-hmm. Yes, quite impressive. And well, not only in Japan, but also in Canada and other parts of the world, the seismic effect is also important.
Yep.
In these studies, have you considered the influence of seismic activities?
No. Basically, over most of the life of an MSE wall, it's not feeling seismic. So that's why when I use the term operational conditions, that's when the wall is sitting happy and not being shaken about. So the way that the recommendation in AASHTO is that you design the wall for static conditions, and if the wall fits the caveats for that allow you to use the stiffness method, you go ahead and design the wall. Then you start thinking about seismic. I don't have a slide here, but for situations in which you have competent ground conditions, it's the soil's not going to liquefy, and you don't have a building sitting on top of your wall, etc. And the peak ground acceleration is less than about 0.4 g. Then there's a simple way of just adding an additional tensile load to each layer, and then you can check your design that way. But that's just looking at the model itself. It doesn't really tell you anything about probability. There are lots of programs that are around now. They're GeoStudio and Rock Science that you can use modified limit equilibrium slope methods, if you like. You can introduce into those programs, a design horizontal acceleration, and you can do your analysis using those type of approaches.
Okay. Carla, any questions?
No, I think there is no question. There are no questions from the audience, but I have one question. I used to carry out probabilistic analysis some years ago, and one of the difficulties was to define the standard deviation, the distribution function, because we used Monte Carlo's method. So in the approach you presented us, you told us there is no need to use Monte Carlo method, but do you see any limitations from the approach you presented today?
If you can use Monte Carlo simulation to do everything that I showed you, you'll get the same result if you have enough realizations. Okay, it's the same mathematics. In fact, we have done that many times because your question is, very legitimate. People ask the same questions, but the mathematics, the theory behind the equations that I developed for you, that I showed you there, give you the same result if you use Monte Carlo. Now, the caveat on that statement is that the distributions have to be log normal.
Okay.
Now, sometimes when people are doing Monte Carlo simulations, they like to use other distributions. They might use like a normal distribution. They might use a beta distribution or a gamma function or whatever. But first of all, what we found and proven actually statistically is that a log normal distribution is actually more accurate. But you could still use other distributions, and you could get different outcomes. Okay, so there's no disagreement with people using Monte Carlo, like experts like you.
Okay, thank you. I have another question. How has the use of probabilistic methodologies been in Canada, in the engineering field?
People like in general, particularly on our West Coast, we have great seismic risk. So all geotechnical structures in seismically active parts of Canada have to be designed for earthquake, and that means that spectral analysis and all the rest of it have to be considered, and then this data loaded into programs. Typically, like I said, limit equilibrium based slope stability type programs are the approaches that are preferred. There's a little bit of seismic stuff happens up in Quebec, but most of it is on the West Coast.
Okay, thank you. There is one question from the audience, Professor Enio.
It's Bernardo. The question is, in your opinion, are we going to be able to integrate all predictive models for soil structure, climate change, and so on, and come up with a feasible reliability-based design?
I if you can take a snapshot in the future and tell me what you think the properties are for the soils, for example, and what the accuracy of the model is going to be, and what the nominal load values and resistance values are, then I just do the same calculations. So I think that the question is not the methodology that I showed. The question is, how will all the inputs change, for example, at the end of the century, if I wanted to carry out a similar design? So that's a little bit beyond the scope of what I showed today. And people are looking at that now, because particularly in Canada we have our problems. You guys do too, but in Canada we have this permafrost melting business where we have huge collapses as the ice in the frozen soil melts, and it just turns to a liquid. And so this is a major problem in the Canadian North. And now my buddies, most of them now, they're all doing research on the Canadian North, trying to figure out what is the impact of climate change on infrastructure in the North. But I'm too old to start another line of investigation.
Okay. Well, Richard, you also mentioned the use of cohesive soils, which is something that is very common in Brazil. So your approach would also be applicable to cohesive soils. That would be no problem in this sense.
Sort of yes and no. Again, there's a lot of fine print when we use the stiffness method, is that if there's cohesion, it has to be guaranteed for the life of the structure, because there's different types of cohesion. For example, if you do a shear box test, even on a granular soil, there's a non-zero intercept right at low pressure, and we call that apparent cohesion. There are other types of cohesions. There's cohesion which is due to matrix suction, etc. And in our stiffness method, we only calibrated our model for cohesive frictional soils as long as that cohesion was there for the life of the structure. We are not advocating to build structures that hold together because of negative pore pressure and then sometime later disappear. That's not a good idea. Mm-hmm. So that's how we treat cohesion.
Mm-hmm. Okay. Any other question?
Yes, there is one more from the audience.
Mm-hmm.
It's from Alan.
Okay, Alan. He's well known to you, isn't he?
Yes. I'm sorry, what was the name?
Alan is my husband.
Oh, your husband, okay.
Yes.
Now, the question, in terms of height, what's the current state of art for MSE wall reinforced with geogrid? A constant vibration effect from a crusher can be an issue. I think he's thinking about the mining.
Yeah, yes. So what happens when you dump large crushed rock on top of a geogrid material? Again, when we calibrated our models, etc., we calibrated on the resistance side for tensile strength. We used an allowable tensile capacity, which is calculated based to include an installation damage factor. Okay, so the method's there, but as I talk, I don't recall in our database that we had materials that you might associate with mine waste or crusher run rock. It was all stuff that you would prefer to use for MSE walls, so smaller stuff. So if you look in AASHTO and you look in the Canadian Highway Bridge Design Code, there are gradation specifications, and our method was calibrated for walls that fell within those bookends.
Mm-hmm. Well, there's a lot of message here congratulating you, Richard, for the.
Is that from my wife and daughter?
No. From Brazilian colleagues here that enjoyed very much your presentation. I wonder if there's any other question.
No, from the audience, maybe I have one question. What lessons can we take to other engineering fields in terms of reliability analysis? Because it works very well. I think it works in different fields, but we still have some difficulties and we don't use this very much because of the limitations. So if you have, what lessons could we take?
Well, I think, first of all, as a general statement, I think that whatever methods you're using now, they may be analytical, they may be numerical. You can always do those calculations with a probabilistic view. Okay, there's nothing magic about that, and I firmly believe that by doing that, you get a better feeling. I mean, let's face it. If someone tells you have a factor of safety of 1.5, I don't think that's as useful as selling someone, okay, if you use this design, there's 1 in 1,000 chance that you will not have a factor of safety of 1. You'll have a factor of safety less than 1. To my brain, I think that's more useful. Mm-hmm. We have a lot of experience that says if you design for a factor of safety of 1.5, we don't have any problems. And that's true. But I don't think it's quite as nuanced. So I think that the way in the future is going to be probabilistic design, and we'll be able to do it because we have the computer resources and power and programs to do it now. In the olden days, we didn't. So I think that's how we're going to move forward. The one thing that this MSE wall business has is that we were able to integrate notions of model accuracy. And that's something that a lot of other geotechnical structure interaction problems don't have. The one example where they do have this type of model accuracy is in pile design, right? Because, there's lots of pile load test data. So you can do the same thing with pile data. And actually, we're doing that. But what's unique about what we have done is that we have combined 2 sources of uncertainty. I think you got the message. One is the uncertainty at time of design, assuming your model's perfect. And then we've integrated estimates of the impact of models that are imperfect, which in our geotechnical business, there's quite a lot of those. Okay. So I think that's the advantage of what we've done. But again, if you go, these companies like GeoStudy and Rock Science, they have these type of things in them. And the Rock Science people, and I have to declare a conflict because the guy that does all that Rock Science stuff is my former PhD student, Sina Javan-Kostel. They have programs now that for MSE walls, you can choose what design method you want to use. And then they have these modified slope programs that will do all sorts of probabilistic stuff. So the tools are fabulous. I wish I had them because when we were developing these methods, we didn't have these tools.
Mm-hmm. Okay.
Thank you.
Okay. So I wonder, well, do you think we should close the session, Carla?
Yes.
First, I would like to thank again Richard,
Yes.
this presentation. It's a great pleasure for me to take part in this webinar. I think it's a lot of information and very good for our Brazilian engineers to have this kind of experience with such a long time that you have been doing research on reinforced soil walls. So I pass to Carla to close our session.
Okay, I just like to thank you, Professor Richard, for the excellent lecture, and Professor Enio for moderating the session. It is for me a pleasure to be here with you because you were my supervisors in my doctoral studies, and Professor Enio since I was an undergraduate student. So for me, it was remarkable. So I just like to thank you all and thank all our audience to be here with us. It is late in Brazil. It is 8:40 p.m. and people are here with us. So just thank you.
Yes.
Oh, thank you, the audience. Thank you, Ennio and Carla. It's nice to see both of you again, by the way. And hopefully I'll see you in the flesh sooner than later. So thank you again. And again, I will send you a PDF that you can give to the attendees.
Okay. Thank you, guys.